we see an sample problem. So it says a uniform magnetic field B with magnitude 1.2 milli Tesla is directly vertically upward through the volume of the lab chamber. A proton with a kinetic energy 5.3 mega eV enters the chamber, moving horizontally from south to north. What magnetic deflecting force acts on the proton as it enters the chamber? The proton mass is this one. Okay, neglecting the Earth's magnetic field. Actually, the Earth's magnetic field is quite large, but actually we just ignore it here. So here we can see we have the magnetic field, the blue dot. The blue dot means pointing out of the page. This means pointing out of the page. Out of the page. Okay, if we use a circle with a cross like this is pointing into the page. Okay, so out of the page, into the page. So this direction, into the page and out of the page. Okay, so yeah. Okay, so here the B field is pointing out of the page, and then this proton is moving to the north, and so according to the Lorentz force, we know B cross B, you use a forefinger pointing to this direction, and then you cross to the B field out of the page, so it will be something like this. So your thumb will point to the right side. Okay, so B cross B pointing to the right side, and this is a positive charge, so the Lorentz force also point to the right side. Okay, so this is easy here. So actually, now we don't really know the velocity itself, but we know the kinetic energy of the charge of the proton. So actually, from classical mechanics, you know the kinetic energy is half of mv squared. Half of 1 mv squared. So you know V should be 2k over m. 2k over m, and then take the square root for the whole term. So this is 2 times 5.3 times 10 to the 6th power. And then this is mega eV, this is not joule. So we need to multiply it by 1.6 times 10 to minus 19 to convert it back to the joule. And then all over 1.67 times 10 to the minus 27. Then take the square root for the whole term, like this. So we know V will be nothing but 3.2 times 10 to the 7 meter per second. Okay, so we know the velocity, then it's fine. And okay, so the Lorentz force Fb, the magnitude of the Fb will be Q times Vb times sine of phi. So Q will be the elementary charge for proton. So it is 1.6 times 10 to minus 19. And then times the velocity, 3.2 times 10 to the 7th power. Okay, so magnetic field here is 1.2 millitesla. Yeah, okay, so Tesla. It seems that I have not mentioning the SI unit for the magnetic field is Tesla, right? Okay, so Tesla. So nowadays, you know, the Tesla will be the brand of a car. Yeah, from the Elon Musk. Yeah. So sine of phi, because they are perpendicular to each other, sine of 90 degrees. I just keep everything here. Actually, if you're very familiar with it, you know, as long as the B is perpendicular to the magnetic field or to the B field, then you know you don't need to bother about the sine of phi like here. So yeah, so actually it is a 6.1 times 10 to minus 15 Newton. Okay, yeah, so this is the force. This is the force. And actually, out of the scope of this sample problem, if you just calculate the acceleration of this particle using the Newton's second law of motion, F equals ma, so you can just plug in the number 6.1 times 10 to minus 15 over 1.67 times 10 to minus 27. So this is a 3.7 times 10 to the 12 meter per second square, so which is a very, very large number. Compare with the G, you know, 9.8 meter per second square. So this is 10 to the 12 power. This is 10 to the 12 power, which is really, really large. Much larger than the gravitational force, of course. Okay. Okay. So actually, it's still the scope of this problem. Just here. Okay. I just copy it here. Sorry. Okay. This. Yeah. Oh. Oh. Yeah. Great. Okay. Yeah. So yeah, like this. Great. So this is the acceleration of the proton compared with this gravitational force. Okay. So okay, this is a JavaScript, I think. So we cannot I cannot demonstrate it now because it is already not supported by the Chrome or whatever. But actually, yeah. So I just skip it now. Okay, so the next topic is the cross field. Yeah, so the cross field means we have two fields which are perpendicular to each other. And of course, in this course, what you have learned is the E field and the B field. So here it means the B field and the E field are perpendicular to each other. And of course, they are uniform. So you can slightly see in here. So the B field is the green cross, which means the B field is pointing into the page, and the E field is pointing downward. E field is the blue arrows, which are pointing downward. So they are perpendicular to each other, of course. And of course, you should have known that the uniform E field is generated by parallel charge plate. So yeah, but for the B field, how we can generate it, you will probably know one chapter later. Okay, but you just yeah. So it's only assumed that we can really generate the uniform B field somehow. And here it says a modern version of the J.J. Thomson apparatus for measuring the ratio of mass to charge for electron and electric field. E is established by connecting the battery, blah, blah, blah. And then the B field also is also set up by means of a current in a system of coil. not shown it here, because if it is shown here, it will actually block this part. So it's not shown. So the magnetic field shown is into the plane of the figure, as represented by the array of x's. I don't know how to pronounce it. So which resemble the further end of an arrow, feeder end of an arrow， 就是那个羽毛，就是那根箭后面的那个羽毛，就是用一个交叉来表示。So the charge particle move through a region of containing both E field and magnetic field. It can affect both electric force and magnetic force. So in some hardcore physics, they will tell you that it will be electromagnetic force, rather than telling you, this is electric force, that is magnetic force. Usually they will just combine them together, simply by this F equals QE plus QV B. And if you need to write it in a vector form, it will be like F QE vector and then V cross B, something like that, or Q times E plus V cross B, something like that. So this is the electromagnetic force. Okay, so when two fields are perpendicular to each other, they are said to be cross field. If those are in opposite direction, one particular speed will result in no deflection of the particle. Yeah. So there will be something strange here. There will be something interesting if the ratio, yeah. Actually, you can see here for this equation, you can see this term and this term add together. So there is a chance that this vector can cancel this one, so that the force will be zero. So this is a special case. Here it mentioned about this. If the forces here, this is one force, this is another one, are in opposite direction. Yeah, so there will be something interesting here. Okay, so just mention a bit about the cross field, and here is another example for the cross field. So this is called the Hall effect, which is a well-known experiment to show the moving particle in the conductor should be negative charge rather than positive charge. Because in the past, you can simply imagine that if you regard a wire, we have positive charge moving upward, which is quite similar to negative charge moving downward. In many sense, it doesn't make much difference. So, and at that time, they don't even know there will be electrons, something like that. So at that time, they define, so they usually assume the moving charge in the wire will be positive charge, and that's why the direction of the current will be opposite to the moving direction of the electron, something like that. So at that time, they tend to believe that the moving charge will be positive charge. But this experiment is important to show that this is not true. This is not true. It should be like that. It should be like that. So here it says, as we just discussed, a beam of electron in a vacuum can be deflected by magnetic field, and the drifting conduction electron in a copper wire also deflected by magnetic field. So in 1879, 100 and almost 150 years ago, so Edwin Hall, then 24-year-old graduate student at the Johns Hopkins University, show that they can so this Hall effect allow us to find whether the charge carrier in the conductor are positively or negatively charged. Beyond that, we can measure the numbers such as carrier per unit volume of the conductor. So this is play with some equation. Okay, So here let's see this figure. This is yeah. So it says figure A shows a copper strip with width D. So this is the width carrying a current I, whose conventional direction of the top current, whose conventional direction is from top of the figure to the bottom. So here we still use the conventional definition for the current. We assume there is a current going from top to bottom. Okay, so there may be chance that positive charge going from top to bottom or negative charge going from bottom to top. So here the charge carriers are electrons, and as we know, they drift with drift speed Vd in the opposite direction from the bottom to top. Of course, we know now, but yeah. Okay, so as time goes on, electrons move to the right, mostly piling up on the right edge of the strip, leaving the uncompensated positive charge in the fixed position at the left edge as shown in B. So the strange thing is like, so if we don't have if we don't have the magnetic field outside, then there is nothing special. Then the charge goes just goes following the direction of the E field. But here, as much as the current is going from top to bottom, and we put an external B field perpendicular to the wire. In here, we have the B field pointing into the page. So, of course, now we know the charge is negative. After finish this, I will tell you why it can't be positive charge, but you should first follow this argument. So here, assume it is a negative charge, which means the velocity is pointing upward, right? So V cross B, so it should have Lorentz force because it is a charged particle moving in the B field. So it should there should be some Lorentz force acting on this particle. In this case, V is pointing upward, B is pointing into the page. So V cross B pointing to the left side. V cross B pointing to the left side, right? And it is negative charge, so FB should point to the right side, which means that the charge will tend to go to the right side. And then more and more charge will accumulate on the right side, right? Okay, so in this figure, it says there will be more and more negative charge accumulate on the right side. And of course, the wire should still be electrically neutral because if it's a current, there can be some charge accumulate inside. But in this case, as much as negative charge accumulate on the right side, which means the same amount of positive charge is accumulate on the left side to balance the charge, which still maintain the electrical neutral. In that case, this positive charge and negative charge will generate a E field inside this wire. So the E field pointing from the positive charge to the negative charge, which means to the right side. Okay, so interesting things start to happen, which means that we have FB pointing to the right side, and this is a negative charge, and the E field point to the right side. So Q times QE will be point to the left side because this is a negative charge. So the Coulomb's force should be opposite to this direction. So FE point to the left side. And interesting thing is that the FB should maintain the same because the VD doesn't change. And if more and more charge accumulate, then this E field will become larger and larger, stronger and stronger. So that at the beginning, VE is small, FE is 0, and then FB is a constant, and then more and more charge accumulate, then FE become larger and larger until they are equal to each other. Then there will be no force acting on this, no net force acting on this particle, and then the charge will not accumulate at the right side anymore. So this is the interesting things. Okay. And this is called the Hall effect. And in fact, the experiment is that if he just puts some current going from top to bottom and then put some magnetic field outside, he can really measure the potential difference between the left side and the right side. So this is so-called the Hall effect. So when a uniform magnetic field B is applied to the conducting strip carrying current I, with the field perpendicular to the direction of current, a Hall effect potential difference is set up across the strip. Okay. So let's do some simple calculation here. And the electric force Fe on the charge carrier is then balanced by the magnetic force Fb on them. So the number density n of the charge carrier can then be determined from V equals Ed, because we assume the E field is uniform, so V equals Ed rather than a complicated line integral. So V is nothing but, let's see, V QE. Oh yeah. So this is the force. So as much as this is another condition, which means that this force, the magnitude of the Lorentz force and the magnitude of the Coulomb's force should be equal to each other. So this is the Coulomb's force, this is the Lorentz force, and they are all the way perpendicular to each other, so we don't bother about the sign of phi, something like that. So this is QE, this is QVB. So Q and Q can be cancelled because it is actually the same charge. So we have E equals VdB. Okay. So Vd also equals J over Ne from the last chapter. So and of course J is also uniform. So we have I equals JA. J is the current density. So J equals I over A. So we have I over NEA like this. Okay, of course we can just plug in Vd to here. So we will probably have E equals Vd is I over NEA times B, like this. Okay, and then this one can also put in here. So we have V equals E is I NEA D. This is E times D. Actually, this is nothing but V, but we can just plug in all the values here. So actually, from this equation, we can actually get this one by, let's see. We can just put n to the left side. So we have n equals V to the right side, so it is at the bottom. And then BI here. And then we still have something like D, E here, AD, something like that, AD. So A is the cross-section area, and then the D is the width, So L should be the length of the wire. So L is A over D. So we have A over D here. So we have equals BI VEL or VLE here, like this. So we get this equation, which means that actually we can get B field, because B field is what you generate outside. So you can measure. I is the current, of course you can measure. E is the elementary charge, of course you know the value. And then the length, you can measure it by a ruler. and then V is the Hall effect potential difference. Of course, you can use a multimeter to measure the potential difference. So in that case, you can build up an experiment to calculate the charge density inside the wire. Okay. So when a conductor moves through a uniform magnetic field B at the speed V, the Hall effect potential difference V across it is capital V is a potential difference equals V times BD. How we can get it? So this one is the V, so we don't plug in here. So we can have a V equals E times D, and then E equals VD times B. So VD times B times D, which is actually this one. So when D is the width perpendicular to both velocity and field B. Okay, so this is the Hall effect. And actually I can also mention that if it is a positive charge, then there will be some conviction, because if you assume there is a positive charge going downward, so this is the VD. Okay, so here, V cross B, V pointing downward, B into the page. V cross B. So V cross B pointing to the right side. V cross B pointing to the right side, and also FB also point to the right side. Right? So in this case, the positive charge accumulate on the right side. So we have positive charge, negative charge on the left side. And in that case, in this case, FB pointing to the right side, and then E field like this. Okay. See. V cross B, FB. Okay, so the E field. Let's see. The E field should be pointing to this side. Okay. Okay. So FE. Okay. Let me see. VD F B cross B pointing to the right side. Do I miss something? VD pointing downward, VB pointing downward, FB positive charge, and then FE. Yeah, so okay, I guessed up a bit here, so let me think it, and I try to let you know a bit later. Yeah, so let's give it for now. Okay, so here, here's an sample problem. Okay, so okay, so here is a solid metal cube of the edge length D equals 1.5 centimeter, moving in the positive y direction at the constant velocity of magnitude 4 meters per second. Okay, so the cube moves through the uniform magnetic field of the magnitude, blah blah blah, in the positive z direction. So this is the B field. This is the direction of this velocity. Okay, so which cube face is at the lower electric potential, and which is a higher electric potential because of the motion through the field? Okay, so here V is here. Okay, so this is V, and then which means that which means that the E, which means the negative charge, is moving upward. And then V cross B should point to the right side. V cross B point to the right side, which means that the FB should point to the left side. FB should point to the left side. And of course, the moving particle is the negative charge, so which means that for the left side, it is a negative charge. For the right side, it is a positive charge, like this. Yeah. Okay. So next, what is the potential difference between the phase of the high and lower electric potential? So we can only use the equation as V equals small v times B times D, which is okay. So V is 4 meters per second. So this is 4 times magnetic field is 0.05 Tesla, and then times 1.5 centimeter, which is 0.015. In this case, this is 3 millivolt. Yeah, a small potential difference between the left plate and the right plate. So this is negative, this is positive. So if you use a multimeter to measure this side and this side, then there will be 3 millivolt. Okay. Okay, so let's stop.